Let's briefly talk about how integer numbers are represented in binary. We have two widely used encoding standards: unsigned encoding for unsigned integer and 2's complement for signed integer. Unsigned integer represents zero and positive integers, and we use unsigned encoding standard, which is simply using power of 2 calculation. For example, 8-bit number 10000011 has ones at bit number 7, bit number 0, bit number 1, and bit number 0. And 2 to the 7 plus 2 to the 1 plus 2 to the 0 is 128 plus 2 plus 1 equal 131. So this binary represents 131. Signed integer represents negative, 0, and positive integers, and the most widely used standard is 2's complement. 2's complement standard is exactly the same as unsigned encoding, except that the most significant bit is a signed bit, and that represents a big negative value if it is 1. For example, in previous example, 8-bit 10000011, signed bit is 1, and it represents negative 2 to the 7. Therefore, it represents negative 125 instead of 131 when we use the unsigned encoding. When signed bit is 0, the bit pattern represents the exact same value as the unsigned encoding. Let's practice converting decimal to binary using the integer encoding standard. First, let's consider a positive integer to 8-bit binary. In this case, we use a classical method of continuous division by 2 until the remainder becomes either 0 or 1. Then we read remainders from bottom to top. So 128 decimal is converted to 10000000 in binary using unsigned encoding. What about the negative integer negative 128? We encode it using 2's complement, but the previous method does not work because we have to take care of signed bit. Luckily, there's a simple 3-step trick. First, we get a bit pattern for positive version, 128 in this case. Then we have 10000000. Next, in step number 2, we flip all bits and we get 01111111. Finally, the step number 3, we add 1 to it. Then we get a final binary number for negative integer negative 128. Let's think a little more about the integer encoding standard. For unsigned integer of W bit, the minimum value we can represent is when all bits are 0. And maximum value we can represent is when all bits are 1s. For signed integer using 2's complement, the smallest value we can represent is when only signed bit is 1, which represents a biggest negative value. The maximum value that WB 2's complement standard can represent is when all bits except signed bits are 1s. One thing to note is that negative 1 is always represented as all 1s regardless of the number of bits. Let's talk about signed extension versus zero extension. For signed integer, we use a signed extension to retain the same value when we convert it to a bigger data type. Signed extension is simply making copies of signed bit to fill extra bits on the left. Unsigned integer use zero extension to retain the same value. Zero extension is to simply fill extra bits with the zeros. Here's an example of sign extension. Basically, we are putting a 2-byte short type integer to 4-byte integer type. As you can see, sign bit is replicated to fill extra bits on the left. So this is a sign extension.